So in this video, I'm working through the second half of the Intro to Volumes worksheet. And we'll get into some shell method and some cross-sectional methods. So in this one, actually, find the volume of the solid obtained by rotating R around the line y equals negative 2. So I've drawn the picture. Just a reminder, in this worksheet, we're using the same region for every problem. We're just rotating it differently or creating it differently. So this is just a little reminder that the boundaries for R are y equals x squared, this little line here, y equals 1, which is this line right here, and then x equals 0, which is, of course, the y-axis. So we're always doing something to this region. In this case, we're taking R and we're rotating it around the line y equals negative 2, which is, of course, that line right there. So again, the first question we ask is the inside, there's the edge of the region touching the line of rotation, and clearly it's not. There's the inside edge of the region, and here's the line of rotation, and they're not touching at all. So that means there's going to be a hole in the middle. Now, which means if we're using the disk washer method, we would use the washer method because there's a hole. So in this case, though, I'm going to use the washer method because we'll show you how that's done. But I'm also going to use the shell method for this one to compare the two. So the washer method. Remember, we immediately know that since it's a washer, we're going to go pi times big R squared minus little r squared, and then we need to come up with the either the dy or dx. And again, how do we know that? We look at this and we picture one washer, a bunch of washers piled up, and you could tell that they're being piled up this way horizontally. So and again, with the disk washer method, when you're rotating around the x-axis, that means that the washers are going to be stacked horizontally instead of stacked vertically. So that means the little bit of thickness is going to be is going to be a little change in x. So this is going to be dx, which tells me my limits of integration have to be in terms of x, and we're going from 0 to 1 here. And the expression has to be in terms of x. Okay. So now the washer method, again, what we need to find is a big R, which is the length. And let me grab a different color here. The length from the line of rotation to the outside edge. So there's a couple examples of big R, and we can see once we do a couple of them that it doesn't change no matter where we go in the region. The outside edge is parallel to the line of rotation, so the big R is not going to change. So in this case, it's going to go from 1 down to negative 2, so that's a total of 3. We put a 3 in there. Then we need to find the little r. I think we're using green for little r, I forget, but that's what we did last time, I think. So notice when we draw the little r, it is changing. And it's changing dependent upon that line, the line y equals x squared. So now we just got to figure out how to describe that line. Well, you can tell that from here to there is 2, of course. And then from here to there, that is just the y coordinate of a point on this line. And we know that that point right there, for example, could be described as x comma x squared. So therefore, it looks to me like little r is going to be x squared plus 2. And so notice so far on most of these we've been doing, well, of course, we're dealing with the boundaries of x squared, but they're pretty easily done integrals, and I haven't been doing the integrals themselves. I don't want you to get the impression that you don't do that, but because you do, you have to finish the problem by doing the integral. But I'm trying to work through the setup right now. That's what we're trying to learn. So, of course, you do this integral. Oh, there's thunder going on outside. So this would be 9 minus, and of course, x squared plus 2 squared. That would give me x to the 4th plus 4x squared plus 4. And this whole thing times dx. And so anyway, you can do that. You know how to do that. Okay, so now I'm going to show you the shell method. So we can use any place we can use the disk and washer method, we could potentially use the shell method. And sometimes they'll be about the same. And sometimes one will be a lot easier than the other. Either easier to visualize or easier to integrate. So one thing you need to learn about, first of all, is if you're using the washer shell method, they're always going to be the opposite variable. So if in this case, we used x for the washer method, that means that the shell method is going to be in terms of y. So that's always true. And I think, and if you've watched the Professor Leonard video on shell method, he talks about that too. He says it in a slightly different way, but that's one thing to just kind of get clear in your head right now. And you'll see why in a minute, but that's always true. And that's one of the reasons why we have the two methods, because sometimes we set up an integral in terms of x and it's not doable, but if we switch it into terms of y, it is doable, or vice versa. So anyway, here we go, the shell method. So the idea of the shell method is, if you watch that video, is, and in this case, I'm going to draw the other side of this thing. So if I go down here, just so you can kind of see it for a moment. So this is like a cross section of the shape. If we're rotated around the line, y equals -2. When we're talking about a shell method, we're talking about, let me draw something in the same place here. We're talking about, the reason why I call it a shell, because it's this little thin shell with a wee little bit of thickness. And so, again, just like in the washer method, we had to find the area of the volume of a bunch of little washers and then stack them up, and integral runs through all of them. In this case, we're finding the volume of a bunch of these shells, and it's kind of like, I don't know if you guys have ever seen nesting dolls. In fact, if you haven't seen nesting dolls, let me show you a picture of one real quick. Here, if I go over here, that's a nesting doll. So these are, I think they're originally from Russia, but I don't know. But my mom used to have one of these. So basically, there's a doll within a doll within a doll. And this is a great example of the shell method, because you can see the shells. So this is an example of a shell right here. Then there's another shell inside of it, another shell inside of it. Here's a shell on the outside. And you can see that all together, if these shells were right up next to each other and filled the whole space, you could find the volume of this thing by finding the volume of each one of those shells. And notice that the shell has a height, and it has a little bit of thickness here. So that little bit of thickness is going to be my dx or dy, and we'll have to find the area of this thing opened up times that little bit of thickness. And notice if we were to slice this right here and open it up, it would actually just be a big rectangle with a little bit of thickness, which would make it a prism, right? And in the Professor Leonard describes the method for finding the volume a little bit different than I am, and of course he comes up with the same formula, but so you should be able to look at the two and kind of match them together. But so notice when we pull this thing up, and so this little bit here is going to be either dx or dy. This is going to be the height. That's that piece right there, right? And then this piece along here is actually just going to be the circumference of the circular part of the shell. So this would be just 2 pi times r, where r would be the distance from the middle out to the wherever that shell is. So there would be an example of this r for that guy there. Okay, so you can see that if I'm trying to find this volume, the volume of this thing is going to be 2 pi r h, and either times dy or dx, whichever direction we're going. Okay? And also, this is something that Professor Leonard points out, generally the h is going to have to do with the shape. It has to do with the curve that's forming our region, and the r is usually going to be dealing with just x or y. Now, in Professor Leonard's video, he said it's always just x or y. But actually, the truth is that sometimes, in his video, he was only doing regions that were touching the line of rotation. So if the line's not touching, or if the edge of the region is not touching the line of rotation, then it's going to be, r will still be something involving x, like x plus 1 or x minus 5 or something like that, or y plus 1. So anyway, that's too much general information. Let's go back to the specifics. Okay, so in this case, we know that we're going to use the shell method, so we're using pi times, 2 pi. Oh, so remember we said that the volume was 2 pi r h by a little change in something, x or y. So I'm going to set up my integral like this. I'm going to put the 2 pi on the outside because that's a constant. Then I need something for the radius and something for the height. Here's my radius, here's my height. And in this case, notice where the thickness is. The thickness is running with the y-axis. It's a little change in y. So this is going to be dy, which means everything has to be in terms of y. The region is still from, the y's are going from 0 to 1, so this is 0, that's 1. And now we need to find out the radius and the height. Now the height, let me use a different color here. The height is going to be that line right there. That's the height of the shell. And you can tell that that height, that line is controlled by the curve, right? And again, if we use that same method of looking at the coordinates of that point, now we're in terms of y, so we're going to write it as square root of y, comma y. That's the coordinates of that point. Okay, so we got the height is this little blue line here, and like that blue line is represented with the x-axis, or the x-coordinate, right? Because the x-coordinate is just how far you are from the y-axis. So that means the height would have to be just the square root of y. And then we need the radius, and the radius is just from the line of rotation to the edge of the shell. Now, Professor Leonard talks about that the radius is actually from the line of rotation to some point in the middle of the shell. It doesn't really matter that you come up with a specific point, because the thicknesses of when we do integration, the thicknesses, we get an infinite number of shells and the thickness goes down to 0. So we're just going to pick this edge here, whatever it is. So it's from here to some point on that line. And of course that distance, notice, is made up of two pieces. There's this piece here, which is just 2. Then there's this little piece here, which is just the y-coordinate, so that would just be y. So this is just going to be y plus 2. So you can see the two integrals that we come up with. Let's see, that would be y times the square root of y, which would be y to the 3/2 power, plus 2y to the 1/2 power, all dy. Notice both these integrals are pretty doable. This one probably is a little bit easier, just because there's less things, but both of them are just a power rule, so it's not a big deal. All right, so that's washer method and shell method. Okay, letter G, find the volume of the solid obtained by rotating r around the line y equals 1. Okay, so we're going to again draw our little region. and the line y equals 1 is right along the edge here. So in this case, we ask the same question we always do: is the line of rotation touching the... you can really hear the thunder going crazy out there. Is the line of rotation touching the edge of the region? And it is. So this is going to be, if we're doing the wash or disk method, this would just be a disk because there's no hole in the middle. So we just need pi times radius squared. And in this case, once again, the disks are not stacked on top of each other, they're stacked next to each other. So the thickness is going to be a little change in x. So this would be dx, which means we're doing it in terms of x. So that would be 0 to 1. Now, the radius, of course, if we erase this for a minute and just draw one radius from the line of rotation to the outside edge, that's all we need. And that, of course, is dependent upon x squared. But notice it's not x squared. Well, let's just look at the coordinate again. So this coordinate in terms of x is x comma x squared. But notice x would be that line right there, and x squared would be that line right there. So the line we're looking for isn't either one of the coordinates. It has to do with the y coordinate. So notice this is always the hardest one for people to visualize. So let me bring in some extra color here. So that line right there is x squared, because that's the distance that represents the y coordinate. Okay? And then if we do a different color, like red, this whole distance here we know is 1, right? So notice that the blue that we want plus the green equals the red. So to get the blue, we're going to do red. We're going to do red minus green. So that would be red is 1 and green is x squared. 1 minus x squared. So that would be the disk method. If we want to do the same problem using the shell method, just again so you can see the difference. In the shell method, let's get those radii out there. So if we draw the other half of this thing, because they're rotating around, that's kind of, this is, again, the cross-section area. So one shell would be like here, with a little bit of thickness. Notice once again the little bit of thickness is in the y direction, so that's going to be dy. So we'll do 2 pi, and we need a radius and a height and dy. So the radius, or the height is just going to be this line right here. And notice that is just the that's just the x coordinate, isn't it? But we're doing this in terms of y. So now I want this point to be represented by the square root of y comma y, because that's where we want this in terms of y. So notice that distance is just the x coordinate, which would be the square root of y. And then the radius is this part right here, which is actually the same thing as the radius before, isn't it? The radius is going to be, so if we use the same color as we did before, the whole line is red. The thing I know is green, and the thing I want is blue. So notice that once again the blue is red minus green. So that's going to be 1 minus y, because the green is the y coordinate, and in this case we're calling that y instead of x squared because it's in terms of y. And that put on my little limits of integration, and I got the shell method. So again, you can see these are two different integrals, but they produce the same answer. Okay, so find the volume of the solid obtained by rotating R around the line y equals 4. So we got one more here. Boom, boom, boom. Oh, I'm going to change it to a different color. I don't want to do red for too long. It's a little bit startling. I like the color red, but okay. So there's green. There's my region, and we're going around the line y equals 4. So that'd be up here somewhere. So that'd be 1, 2, 3, 4. So that distance right there. There's a 3 between us and the region. So this is clear. There's a hole in the middle. Let's do the washer over here. We know that's going to be pi times from 0 to 1 of big R squared minus little r squared. And we're rotating around a horizontal line, so that means my washers are going to be stacked. They're going to be set next to each other, so that's going to be a dx. My big R is going to be from the outside edge up to that line of rotation. And notice that once again, if we do a little highlighting here, that part is my y coordinate. So we want, so the big R is going to be, in this case, 4 minus that little bit right there, which would be the y coordinate, which would be x squared. And then my little r is going to be a little line like that. And that's the same no matter where I draw it, because the inside edge of the region is parallel to the line of rotation. So that's always going to be 3. Boom. So that's a pretty easy washer method. Pretty easy integral setup. Let's take a look at shell and see if it's better or different or whatever. So that's going to be 2 pi times the integral 0 to 1. We're going to have r and an h and a dy in this case. And so let's erase these guys. The shell is going to, let's pick some random shell here. That's going to be my h. And my h is just the x coordinate of that point. And that point, in terms of y, is square root of y comma y. So I'm going to have just the square root of y there. And the radius is going to be from there up to there. So that's going to be same thing I did before. It's going to be a distance of 4. That's the total distance, right? 4 minus that little bit right there. And that little bit is the y coordinate. So I just put y. So you can see in Professor Leonard's video, he talks about the shell method is always just x or y. But if you start moving the line of rotation away from the edge of the region, it's still the radius is always going to be either x or y or something plus x or y or some number minus x or y. So and then the height is always something to do with the function. It's determined by the function itself. So it's going to either be, in this case, it's got to be either x squared or square root of y. Okay. So that's the wash and shell method. Hopefully you're getting a pretty good idea of the two of those. Now we're going to switch gears here and we're going to talk about a different way to create a 3D shape. And this is using cross-sectional areas. So in this case, it's saying the cross-sectional area is a semicircle, okay? And whoops, I didn't say which way these are going. So we're going to say cross-sectional area is perpendicular to the x-axis. So what that means is, and I showed you this in the visualizing video, but what it means is you're going to draw these little lines perpendicular to the x-axis, and in each one of these lines there's going to be a little semicircle that pops up. And I have a hard time drawing these. Let me use a different color. So it's going to look like that kind of. And then this, of course, will be bigger. And you can see a bunch of these little semicircles. They're as you go towards the y-axis, they get bigger and bigger because this bottom line right here is determining the size of the semicircle. So if we take one of these and set it on its side, then you can tell that this distance right here, let me use a different color, highlight it, that is that guy right there. So the size of the semicircle is being determined by something in the region. So in this case, we can tell that the region, what's determining it here, is that top line is 1, the bottom line is x squared. I mean, y equals x squared, right? So we have to figure out whether this is in terms of y or x, but this is going to be 1 minus something to do with the function. Okay, so now where's the thickness of these things? So they're not just a slice, they got a little bit of thickness to them, right? And so you can tell that the thickness is in the x direction, right? Well, that didn't help much, but so this is going to be dx, so that means we want this line in terms of x's. So you can tell that this is just one, kind of like in the ones we were doing above, that line is is 1 minus that little blue piece down there. And that little blue piece is x squared. So this should be 1 minus x squared. So that's the length of that. Now we notice that that's the diameter of the semicircle. So if we want to find the volume of one of these little pieces, we're going to take, that's just going to be 1/2 pi r squared. Where'd that come from? Well, the area of a circle is pi r squared. So this is a semicircle, so we're going to take half that. And then there's that little bit of thickness, and that's where the dx will come in. Okay, so this is kind of like a half of a cylinder. So that's the basic formula for this cross-sectional area because we're dealing with semicircles. So I'm going to write the integral, once again, from 0 to 1 because that's determined by the region. I'm going to put the pi over 2 out front because it's a solid thing. I mean, it's a set thing. And then I just need a radius squared and a dx. Now, that 1 minus x squared, of course, is the key expression here. But notice 1 minus x squared is the diameter of the semicircle. And we all know that radius is half of the diameter. So what's going to go in here is 1 minus x squared over 2. So once again, if we integrate that, we will find the volume of this shape that's determined by the semicircle. Okay? Okay, got one more here. This will be a different type of cross-sectional area. But once again, we're using the same shape. And we're going to do, I think this one will do parallel to the x-axis. And that should be in the instructions. I just left that out. I need to put that in. Find the volume of the solid with R as the base and cross-sectional areas of a square. So this time we're going to draw the lines this way, and we have a square coming out of it. Let me change my pen color for a minute. So we have so there's my base, and be a square coming about, and down here there'll be a smaller square. So you can see that, again, we're just taking the base and we're just rising these squares up out of it, and that's going to form the shape, the volume that we're talking about. And again, if you have trouble visualizing this, don't rely on my drawings. Go back and watch that video where I showed you kind of how these things are formed. So now notice up here, this is the formula for this cross-section area because we're using semicircles, but now we're using squares. So if we take one of these squares out just to look at it, again, that distance right there, whoops, there's my highlighter. That piece right there would be the same as that piece right there. And we know with a square, we just need to know side times side. So this is just going to be something squared, right? So my integral is going to go from 0 to 1. We're going to have something squared. That would be the side length. And once again, because now we're running parallel to the x-axis, that means my little bit of thickness, you can kind of picture it there, right, is in the y direction. So that's going to be dy. So basically we just need to know how long that little yellow line is, right? Because that's going to be our side length, and the area of a square is just side times side. So that, of course, is determined by this line y equals x squared again. We're in terms of y, so we're just going to grab that point right there. So this side is 0, and that side is the point square root of y, comma y. And notice the yellow line is just that square root of y, because that's the distance that's associated with the x coordinate. So this is just going to be the square root of y. Look at that, square root of y squared. So this is a really simple integral. That'd just be from 0 to 1 of y dy. Can't get any easier than that. All right, so that's hopefully give you a good idea of all the methods now. You've seen the shell method, the disk washer method, and the cross-sectional method. In the cross-sectional method, notice the formula changes depending on what shape we're pulling out of the region. So here we pulled a semicircle, so that gave us that formula. Here we pulled a square, so it gave us a much simpler formula, just something squared. There's no pi's involved here because we're not dealing with the circle. If we used an equal out triangle, that would be a different formula. So so these guys change. Notice with the shell method, it's always the same. You're always using this idea that it's 2 pi r times h times a little bit of thickness, d something, right? With the washer method, it's always pi times big R, pi times big R squared minus little r squared, d something. And I'm sorry, that was a washer. That's the disk. That's the washer method, yeah. And then the disk method, remember, is just pi times radius squared, d something. Alrighty.